So in last class, we discussed about um, this one casting. Okay. So what is the use of casting? Two types of castings are there: upward casting, sorry, static casting, and dynamic casting. Okay. Just I want to convert one type of data type to another data type. I will use the static casting. And dynamic casting, we will go for the classes like parent class to child class to parent class, inheritance. That concept we are applying the dynamic casting. Okay, dollar cast we are using that. And then next topic we did discuss about that compiler directives. Okay, compiler directives means we are using tick define, tick include, tick not define. That means some other files we are writing somewhere else. I want to include it, and then some parameters I am taking. That parameters I want to include it. Tick define. So define some parameter width. So then that width only I will use the entire my simulation, and then next topic is related to packages. Packages means grouping. It is like a container class. Okay, whatever the different classes, because in your test bench driver, monitor, scoreboard, generator, and then agent, all these things are written somewhere else. I want to utilize in my same module. So then, in top module, we will execute all these things. Okay. Then I will write one package. In that package, all the signals, all the classes will be included here. Okay. Then we will utilize this package like import UVM package. So scope resolution, some star. Then all the classes will be imported in your top module. Okay. That is the purpose we are using these packages. And then next one, program block. So program block is used for test bench. So see all the components, that means DUT and then the test bench. DUT and test bench same time we want to communicate each other means we will get a trace condition. To avoid the trace condition, then program block we are using. Okay, program block is also like a test bench. But we cannot instantiate test bench in your program block or module in your program block. This program block we are instantiating in our test bench. Okay, so then the test bench will instantiate the program block. This will avoid the race condition because uh, DUT, TP, all these things are executed in active region only. Maximum active region only it is executed. Okay, then we will go for the NV region. But this program block is executed in reactive region. That means all the execution, that means all the updation is completed. Then only it moves to the program block. Then if you are driving writing operation, I am also reading the write operation. Both the at a time we can read it. Okay, because to avoid the race condition, because all the DUT signals are completed, then go for the test bench part. In the test bench part, program block is there. Then this test bench will point to that program block. Then the program block will be executed in reactive region. It will avoid the race condition. Now today we will discuss about parameters. What is the use of parameters? Okay, see basic thing. Whatever the parameters we are using, basically in our module we are using the parameters, right? Uh, if you are not using the parameter means what will happen? Suppose he is doing that operation with 8-bit module, and I want to do to convert into 16-bit. Then again I need to write another module. Okay, so this module is not reusable for me. Okay, and then you want to write 16-bit. Okay, sorry, 32-bit, 8, 16, and 32, and then you want to do 64-bit. Then every time different modules we need to write it, because so that will support only 8-bit, and this one is supposed to 16-bit and 32-bit, 64-bit. And someone want to do that 128-bit means again you need to write that another module. That is the reason we are using these parameters in our module. Okay. Then same module, it will suppose that different modules. Okay, so different sizes of bits we can apply it. Same thing here also. Suppose you buy a Samsung TV or LG TV. Okay, so then I bought 32 inches and he bought 64 inches. She bought 128. So and then large. Okay, so and in this way you are buying. You're changing the TV only, but remote is not changing, right? Remote will be same. So remote will be same for 32 inch, 64, 128 and 256. Okay. So all these things are the device is changing, but controlling is not changing. Okay. Same way the parameters we are utilizing here. So just I am utilizing the parameters. So think of a parameter as a compiler time setting configuration node for modules. Okay. So remember this parameter never change during the runtime. Before the runtime only, we are fixing that some parameter with that with only it is operating. Based on that only it is creating the hardware, right? So you are creating that 8 bit, okay, 6 to 8 bit, okay, and then you are creating for 16 bit, it is fixed to 16 bit. Based on that 16 bit only, it is creating the hardware. Okay, so that is you need to remember that. Okay, so and then see, think of a parameter as a compiler time setting or configuration of for the modules. Okay, and then I'm using the modules like so. How we are writing the module? Basically, module some hash parameter we are taking, right? So this is generally my module name, module some module name, okay, like half adder something you are writing. Okay, inside that you are writing input void a comma b comma a comma b, and then output range. So here I'm writing some comma carry. Okay, so this one is useful for how many bits? This is useful for only single bits, right? Only single bits I will apply here. So now I want to write 4-bit support. Then again I need to write the 3 down to 0 here. And then this one also 3 down to 0 here. Okay. Then again I need to create the another module. Instead of that, we are writing like this module, some hash, okay, parameter. Okay, so your module name also you need to write that half adder. Okay, half adder hash parameter. In this parameter I am writing some width. Okay, so data width equal to I am creating 16 bit. Then every data, whatever the data we are using, so that will be applying for. So data width I'm using some semicolon in this. Again we need to open the brackets and then input we are taking that y, and then width minus 1 down to 0 of a comma b. Now a comma b will be parameterized. Okay, it is a 16 bit because width is 16 minus 1 down to 0 means 15 down to 0, that is equivalent to 16 bit module. Okay, so then each and everything will be 16 bit. AB values are also 16 bit, where it will support up to 16 bit. Okay, so in this way, we are writing the parameter. Then during the TP time, we are using different bits. Okay. Then we can override the bits, right? Based on the tick defines, defparams, and then some constants directly passing. Based on that, we are changing the bits. Same parameter. See, while using this parameter, so without using the parameter, you are writing that module 8 bit, and then if you want to do that 8 bit after that 16 bit, you need to create another module, and 32 bit you need to create the another module. Okay, multiple modules are there. So that is a bad way to write the code. Okay. So I want to parameterize, then I will write in a different ways. Okay. Okay. If you parameterize means it can apply different widths at a time. Okay. See, so one handle, everything will be applied. See, width equal to 8, 16, 32, 64. Same RTL. RTL is not changing, but we are changing the parameter width. How we are changing the parameter width? So you know, right? So module name data width of some 16. Basically, you are writing the 16. After that, you want to change it data width of 32. Okay, in this way, I will override it. Okay, name based overriding. So how we are instantiating the module in our TV? Same way, I can instantiate the parameter in my TV. Then we can write different parameters. So then we will go for different widths. Okay. So compilation time only we will mention the parameter width. See how he is writing that basic syntax for the parameterized module. Parameter my module hash parameter width. Okay. So then we mention the parameter width. We can close the parenthesis and open that another parenthesis for mentioning the input and output ports. Okay. So basically the module we are writing here uh, parameter width. Okay. In this is the single parameter. If you want to write multiple parameters, again parameter some depth you want to write, you can write it. So depth equal to 16. In FIFO, we are having width and depth, right? So here 16 means up to 0 to 15. So 16 locations we are writing the data. In this 16 locations, what is the size of the data? This is an 8 bit. Now someone came, no, the width is not enough for me. You want to change for 16 bit. Okay, again we are changing the 16 bit and then 32 bit. Okay, again I am changing to 32 bit and then 64 bit. Okay, so again I am changing that 64 bit. So in this way we will operate different bits. So this is the instantiation. See, adder hash 8. So DUT 1 and then DUT 2 16 bit, DUT 3 32 bit. Okay, so compiler creates that 8 bit adder, 16 bit adder and 32 bit adder from the same RTL. Just we are instantiating. That's it. Okay, so what is the instantiation? Your DUT module name, hash, and then some bit you are mentioning, and then the user defined name DUT1. Okay, so in this way, I will override my parameters. Then it will be operating for all the parameters. Okay, same thing. Counter also is writing. See, simple counter. How much? What is the counter name here? How many bit counter is this one? Synchronous 16 bit counter. Okay, so because the bit is 4, okay, 4 minus 1 down to 0, that is 3 down to 0. How much count it will support? That up to 16. Okay, because 4 bit to power 4, to power 4 means 16, 0 to 15 counts will be doing here. Okay, so that is a 16 bit counter. Same way, asynchronous they are asking. So asynchronous means so passage clock or negate reset. Okay, based on the reset it will count again. Okay, if reset count equal to 0, else count equal to count plus 1. Now I want to change my counter to 4 bit to 8 bit. Again, the parameter placed right, the width equal to 4. Again, you want to change for 8-bit, you can change it. Your counter module name is counter hash 8 or 4, 16, and then 32. Based on that, it will change the counts. Okay. So name-based parameters, named parameters passing. So this way we are utilizing. Most of the cases we are writing this name-based parameterized modules. Okay, instantiation we are going for the name-based. See, our module also we are going for the name-based only. Position-based means it will be tough for the instantiation because we need to check the input output port same order. If you change means the values will be taken, but it is taking different values. Then we need to check everything. Okay, that would be the problem. Suppose position based means you need to write that A, B, C values are in same order. Suppose inputs are A, B, and C are the inputs, and then sum and carry are the outputs. Same order we need to write that A, comma, B, comma, C, comma, sum, comma, carry. Okay, same order we are writing. Suppose if you are writing sum, comma, carry first, and then A, comma, B, comma, C in the next, then it will get different values. But in the name base dot sum of sum, okay, dot carry of carry, okay, dot A of A, dot B of B. So in this way you are instantiating means anytime we can, so just I want to see all the ports are there or not. Where it is available, I don't think about it. Okay. So just you are present in the class or not. Okay, you sit in the corner or you sit in the front or you sit in the back. I don't think about it. Okay, I don't care about it. Just I want to see all your presence. Okay. So in this way it is taking that. Okay. So same how we are instantiating here, your module name hash dot width of width. Okay, so dot width of width is the 16. Here I am passing to 16. Suppose you want to change it, dot width of some 32. In this way it can change. Then it will support 16-bit count, 16-bit parameter as well as 32 bit, right? So both will support here in this way. Suppose multiple parameters are there. Parameter width and width is 8. And similarly parameter depth. Depth is 16. Suppose you are changing, you have another parameter like parameter address width, because data width is different and address width is different. Address width is 16. And similarly parameter some ID. Based on the ID, I am writing that is a 32 bit. Now, multiple parameters are there. Even though multiple parameters are available, we can instantiate it and then we can override the parameters. See, here I am writing 32 bit and then 1024. Now, this 8 bit also it's working and then it is also working for 32 bit. Okay. So how the FIFO depth and width we are writing. So just simple basic read and write operations I am doing here. Some generic memory. Okay. Module, some memory. Parameter is width is 8 bit and depth is 16 bit. Just I am taking that clock and enable pin. See why you are taking $C log to, so log to the base 2. So $C log to the base 2 of depth. What is the depth here? 60. Then it is changing to what is the value we are changing here? So log C to the base 2. This should be converted to 16 should be converted to 2 power 4. Then what is the value here? 4. Okay. because log to the base 2 value is 1. Okay? Because 2 power 4 power should be converted to multiplication, then we will get the 4 value. Now here 4 minus 1 down to 0 value we are getting. Okay. Sometimes you are taking the bigger value in the parameter and then you want to utilize it for smaller value. Then we will go for the see that parameter is supposed that some powers of bits, right? 2 power 4. See here I am taking the 4 down to 0. Okay, 4 minus 1 down to 0 means 3 down to 0. 3 down to 0 means 2 power 4. 2 power 4 is 16. Okay, that means it is capable to store up to the values 0 to 15. Now you are changing to 64 bit. Then 64 means 2 power 6, right? Then 6 bit value will support. 6 down to 6 minus 1 down to 0. That means 5 down to 0. 2 power 6. 2 power 6 means up to 64 values it will support. Just here I'm doing the write data and read data. Write data is the input, read data is the output. Okay. Now I'm writing the reference memory. In this way, we will consider the reference memory. In scoreboard, sometimes we will take the reference memory. Okay. So this reference memory we are taking here. That means that reference memory stores the expected values, and then actual memory will be there. That will stores the actual values. Okay. So then I will compare that actual values and expected values. Then if it is equal means my scoreboard is passed and then my test bench is also passed. Now same way I am writing some reading operation and writing operation. This is the writing operation. How I am saying that writing the data into particular address and it is stored in the memory. This is my memory. I am mentioning some address that is 1000. Okay, this is your memory. Okay, so I'm writing the data AA, okay, into the location, address location 1000. It will store in the memory. Okay, that is the writing operation. Now reading time, just whatever the write operation you are writing here, okay, that will be reading. That means read data. I'm reading the memory of address value. Okay, so this address value based while reading, I'm not giving any data because I'm receiving the data, right? That is the reason I'm providing the address only. Memory address based on the memory address, it is storing, it is getting the values. Okay, just just for parameterized module and representative. Okay, now this is the 8 bit comma 16 bit. Now I want to change it 8 to 256 or some 32 to 1024 and 64 to 4096. Okay. Now you are changing the values, right? See, 1024 means 2 power 10, right? Then it is changed to 10 bit. Okay. 10 minus 1 down to 0 means 9 down to 0. 9 down to 0 means 10 bits. Okay. So that is the multiple configurations is work for parameter. Same way FIFO. FIFO also I'm using here width and depth. Same width and depth we are writing it. Okay. Global parameters only we can override. Okay. Sometimes I'm considering the local parameters also. Local parameters means here we are writing the module, right? Module FIFO. Inside that I am writing the address width and depth. Okay, these are global parameters. Okay, so these parameters we can override it. And then without rewriting the code, we are converting 8 bit to 32 bit or 16 bit to 32 bit. Okay. Now, local params means, so just instead of parameters, we are writing the local param. Okay, local param. I am using some address width. Okay, and similarly, local param data width. Okay, some data width, address width and data width. And similarly, local param. I am writing what is that? Address depth. Okay, some here also 32 bit and depth is 64 bit and local param data depth. We are using this address bit, data depth, address bit, data bit, data depth, address bit, address depth. All these are local parameters. Within the module only you can use. Outside the module you can't override it because the name itself local, right? So local means within the module. Okay, whatever the module we have, same module we can use it. And then in your TP, these local modules I want to utilize in my TP means it's not possible. Okay. Hmm. Whatever the global variables are there, that only we can reuse it and we can override it. Otherwise, it's not possible. Other parameters are not possible to override it. See, uh, width and double width. So same thing, but double width we are writing. Sometimes I am writing like this 2 into width. Okay, that means width already taken 8 bit, but in my parameters variables I am using like this 2 into width. That means doubling the width. So 8 bit to 16 bit I am changing here only. So just same thing here you are writing the parameter width and depth. Okay, while reading the data and writing the data, so you are writing that some write data, W data. Okay, here width width minus 1 down to 0 you are writing. Instead of that I am writing 2 into width. Okay, so 2 into width minus 1 down to 0. Now it is converted to 16 bit here only because I am doubling the width for my variables. Okay, same thing. The parity bits, the width should be divided by 8. Whatever the width we are taking here, 32 bit. 32 will be divided by 8 means the parity bits will be supporting for 4 bits. Okay. Just same variable I am utilizing, but the width I am not assigning directly. Okay, the values are not assigning directly. The values are considering from some width and depth we are taking, right? So based on that, see previously we are writing C log base 2 of depth. Okay, here the variable I am taking no minus 1 down to 0. Okay, so here C log 2 will decides that width of your variable A. Okay. Based on that, we can also write different parameters. Okay. Type parameter. So type parameter means like data type. You are using the data type integer. Sometimes I want to use a bit. Sometimes I want to use byte. And sometimes I want to use logic. Okay. So for that we are using this type parameter. So type T. Most of the times we are using this T, type T. Okay. This T will decide that integer or bit or byte or logic. Any data type we can apply. Just same parameters I'm instantiating. See, yes, my storage is, my module name is storage. Same storage I'm applying for integer data type, and then same storage I'm applying for byte data type, and same storage I'm applying for uh, string data types or logic data type. Okay, so in this way I will use this type parameter. Type parameters is related to data types. See, string parameters I'm using this name, string name. See, parameter T you are utilizing int and then byte, bit, like this, right? Same way I'm using for the names, string name. This name you want to change for it. Globally, you want to change the name. Sometimes I'm using the HBMP, sometimes I'm using the AXI, sometimes I'm using the APB. Okay, so AXI can write it, or APB I can write it, or AHB I can write it, or I2C I can write it, or SPI I can write it, DDR we can write it. So Ethernet we can write it. In this way, I can change my name. The display will be changing here. Okay, so strings also we can change. And like state parameters, state mission parameters, that means FSMs we are taking, right? So number of states should be 8 here. Okay, so states is 8 means C log 2. So how many things will be there? 2 power 3. 2 power 3 minus 1 down to 0. That means 2 down to 0. 2 down to 0 means 3 bit. So it will suppose that 8 states. Okay. So up to the number of states is 8. See, number of states I am mentioning here 8. The bits will be decided for the state is C log 2. Okay. In this way, I can change that. I can assign my states. See, that C log 2 depth equal to 256. That means 2 power 8. 2 power 8 means address bit will be changes to 8 bit. Okay. Say 8 7 down to 0 means it is an 8. Okay. Same way, different parameters only I am applying different examples. Same examples, multiplexers I am taking. Multiplexer A, B are the inputs and select is also input and single output we are getting. Same thing I am applying here with. That means the multiplexer is single bit to 8 bit I can apply. That means the numbers will be increasing. Capability of storing. Previously 0 or 1 I am storing. Now 8 bit means up to it will store the 256. 100 it can store, 250 it can store, and 101 we can store any number. Okay, that's the beauty of parameters. Okay, and then how we are overriding. Okay, defparams we are using. Define params is the old style of overriding the parameters. Same thing. Just you are overriding for um, different parameters, right? So how I am overriding? Def param, that means define parameter. Dut dot width equal to 32. In this way I can override it. But it is a old style. The new style is recommended for this module name hash width of your new width and then your user defined name. Based on that, it will be overriding the parameter. So this one is preferred way we are writing the different parameter width. See, before transaction is 32 bit. Then I am creating for 8 and 16 and 32. Same class. But in class parameters also we are taking, right? So module parameter, same thing. We are also applying for the class. Class some transaction hash parameter width. Okay. Same way, this can also override it. How I can override it means in your TP, the class name we are writing, like class transaction or class packet you are writing. same thing, I can write that some packet hash. Here the width is 32 bit. I want to change it for 64 bit. Then you can change it. Whatever the class parameter, class transaction you are taking or class packet you are taking, based on the class name, you are instantiating it at the packet, right? Object instantiation is there. So packet PKT, in this way you are assigning that. Same thing, I can assign like this packet PKT, then PKT equal to new, I can assign that this new will be object, creating the object. Okay. So 16 bits it is converting, 64 bit it is taking there. See, these are the parameters we are taking. Okay, data weight, address weight. Okay, so some data weight, address weight, FIFO depth, number of channels, number of bands, cache size, HBM channels, AXID weight, burst length, timeout, different parameters. So what type of parameters are you are using? Width here, simply we are writing the width, and then these two only we are know. Okay, we know, but before depth also we can take just depth instead of writing before, or memory depth, or address depth. Okay, data depth. Instead of that we can write anything. Hmm. Just see this summary. Hmm. See this program. What we are doing here, same parameterized classes we are using. Simple example for parameterized class. Okay, just I will go for the last class. This is last example. Like class transaction I'm taking. This is my class transaction. Normally we are writing like this. Okay, then go for the parameterized classes means, so class transaction hash, the parameter width, we are taking the width is the 32, and similarly I am taking the type also. Okay, multiple parameters are there means you need to write in this way. Okay, comma, just how we are overriding it. What is your class name? Transaction hash. Okay, inside the parenthesis you need to write the uh, width of the width parameter. So 8 bit it will support, 64 bit it will support, and 128 also it will support. Okay, and then type parameter int string here. Okay, so int, that means type data type, whatever the data type we are applying here, integer data type. So id, so idt, that the handle is idt. Idt is that integer data type. See, I am not writing any data type here, just idt I am writing. So instead of bit also you can write it idt. That means it will be bit data type or integer data type, because idt you are using means the id type is integer data type. Okay, and similarly id also I'm using that is also integer data type. Now I'm writing the function void print method, just I'm printing the data, whatever the data, and then id. Okay, same thing. Similarly I can also print my width and data. Okay, so that means width is your width and data is that your data, and also id. id for data type I'm not printing, because data type is an inbuilt, right? So integer, byte, bit, all these things. Now see the module. Module name. Your class name is transaction. I'm taking the transaction. Previously my bit is 8. So here I'm changing to 64 bit. Okay. So this is 64 and integer. So and then now I'm changing my bit data type to, so 64 to here 128. So this is my 128 bit suppose here. And then transaction here 256 I am writing. Now three module, same class, it will support for three different data bits. Now transaction TR equal to every transaction. This is one transaction, this is another transaction, this is another transaction. Okay. Now you need to change that 8 bit to 64 bit, right? This is 64 bit. Similarly, I can change that variables also. AB, Baba, Sunday, and B. Okay. And here also I can change the ID. Okay. And transaction data type also I can change it here. So what is the transaction data type? It is a TR2 is the 128. Okay. So this is 128, and then this 128 data I'm writing here. See, just why I'm taking the underscore here, underscore it will support that 16 bits. Okay, here 16 bits and also 16 bits. Okay, same thing I can copy here and, and pasting. That means 128 bits it will support, right? And 256 means it will support, it will be changed to, suppose smaller value also you can write it, the bigger value you are taking, and then the smaller value also it will take that, just it is appending that some zeros. Okay, so now it is taking that 256. Okay, clear? Just I am printing all the values. Two times I am pasting the same. You got the answer. Double, double semicolon also is not problem. See, width is 64, 128 and 256. Same class. But we are overriding for different widths. See, 64, 128, 256. All these things are supporting. And here data also 256 data we are supporting, 128 and 64. Clear? This is the parameterized classes I am taking here. Okay. Simple parameterized class, now we are applied that both the width and then type also. Okay, so then you can go for the simple parameters like width and type. It's the same example. So this is only width. Same thing, just we are writing the different widths only. Okay. 8-bit width I am taking here class packet. Now 8-bit to 16-bit, and then you can, if you want to write another also you can write it. For how many handles you are taking, those many objects you need to create here. Okay. So otherwise it will not get the values. Okay. Clear? So next one is final block. What is the use of final block? Up to now, you have seen that initial begin block, right? Initial begin block is used at simulation starting time. Okay, most of the times we are simulating it based on the simulation starting time. We are going for the initial begin block, right? Now I am going for the final block. This final block is not taking any. not consuming any time. Okay, so it is executed after the dollar finish. Dollar finish is that terminating the simulation. Okay, any adjustment, any cleanups is needed, then this final block will be taking care of that. Okay, so that's what initial begin is the start of simulation occurs. See, think of final block is a cleanup code that runs exactly once after the simulation ends. Okay, so it's a simulation is ended, then it will go for the final block. Okay, so then when the simulation ends, once exactly it's clean up the code that runs exactly once when the simulation ends. Okay, whenever you call the dollar finish, this dollar finish you called means your simulation will be ended. After that, this final block will be called. Okay, so this block will clean up any codes are there that will be cleaning up and then reporting that. So that report, printing and cleanup phase, this is exactly what final block does. Okay, cleaning up means uh, like in UVM we have some cleanup phases, like reports will be taking place. That means it will run all the tests and collect the statistics, print the report, and closing the files. That is the cleaning up. Okay. So we are seeing the reports, right? Your address is some AA, and then data will be printing. So some table format you are getting the some values. Okay, that all the things will be taken care by this final block. And most of the times you want to see some coverage reports. At that time also I will use this final block to print my reports. Okay. So that is the main purpose we are using the final block. So final blocks executes automatically at the end of the simulation. So exactly once at zero simulation time, it will not consume any time, right? It will not consume any time. Once in the simulation, it will execute it. After dollar finish, cannot contain timing controls, right? If we are calling the dollar finish means we are finishing the simulation. It's ended. Okay, I'm not printing anything. So that's why this final block will be calling after this dollar finish. So then it will report it, whatever the statistics. Okay, statistics will be reporting. And then some printing messages, any printing messages are there, it will print it. Okay, based on that, we are getting some report. See, where does it executes exactly? That means simulation and in time. Okay, whatever the simulation we are starting, initial begin at executes at t equal to 0 time only, right? T equal to 0 time only it is executing. Whenever we are calling the dollar finish, then it will execute the value. Okay. See this dollar finish. See, after the initial begin block at the zero simulation time, the initial block will be running. After that dollar finish we are calling. After that we are calling the final block. Then simulation will be ending. See, dollar finish called at t equal to 100 only. After this there is no time. That is the reason this final block will be executing once in the simulation time, that is ending of the termination. So when the simulation terminated, then it goes for internally it goes here. Okay, and then it will print all the statistics. It will reporting the objects. Okay, so that is the reason we are writing this final block. See, just all the things are writing in your module. Okay, module initial begin, it will start the simulation, that means starting the simulation and calling the finishing. Okay, inside that inside final block we are writing. Okay, that means all the things are completed, then this inside final block will be executed. Actually, you thinking about some final block is also like an initial begin block. So not like that. Initial begin is 0 simulation time, T equal to 0 time only is calling that. And then after simulation is ended, then go for the final block. It will print the statistics, all these things. Okay. What happens internally? See, internally we are writing that initial begin block at 0 at time t equal to 0, then initial will be starting. After that, what is the time period you mentioned? 10. If you are mentioning 100 also, you can mention the 100. Then dollar finish we called. At the same time, the final block also executes. And then simulation will be exist. Okay. See here, the time is consuming that 0 to 100. Okay, so after dollar finish, we are calling here only. Okay, whenever this dollar finish is called, simulation will be terminated. Okay, simulation is terminated. Then only this final block will be executing. Okay, so just like in you are seeing the inactive region, has zero state. Same, same simulation time is executing, but small delays there. Okay. Same way, this final block also, after calling the dollar finish, we will call this final block, and then so how many tests are passed? Okay, statistics. What is that? How many tests are passed? How many tests are failed? Okay, what is your coverage report and what is the goal you reach? Okay, all these things are reporting here. In final block, all the statistics we are getting. See, if you are going for the test, okay, then your report will be showing on the progress card, right? Same thing, all these things. The progress card is the final block. Okay, once you written all these things, then we will see the reports in our progress card. So same thing, this final block also doing that. So summary we will get it. Get always a summary. You always get a summary in a final block. See, simulation summary we are writing here. Dollar display, simulation summary, pass count, and then fail count. You're done 5 simulation or 7 simulations in that. 5 are passed and 2 are failed. Total 7 tests. Okay. Why it is failing? We need to check that. Okay. Multiple final blocks are also we are having. See, same thing, just we are writing the multiple final blocks. So that means you are seeing multiple initial begin blocks. Okay, which block is executed first and which block is executed next, I need to check that. The order of execution we will know based on this multiple final begin blocks. Okay, final blocks. So this final block one is executed first, and then block two is executed next. Okay, so that means so final block one, final block two, or final block two, or final block one. The order may be changed, right? Because he is also executing same time, I am also executing same time. Then I don't know you are executed or me is executing. Okay, the simulation is decision. Simulation decision is it will depends upon the initial begin block. Based on the final block, I will see. Okay, first he got the execution, then he is giving the execution for me. Okay, in that way I will know. Okay. See, coverage reports. I told you, so blocking final block is also giving that coverage report. See, coverage percentage we are calculating. Passed into 100 divided by total test. Okay. This coverage, or we will write that get coverage. Get coverage means we are getting the coverage some 95% or 100%. See, here 100 tests are there, 95 are passed, then you will simply say that 95% pass percentage. Okay, so coverage we are getting 95%. And 90 tests are passed means 90%. So 10 tests are there and 5 are passed means 50% we are getting. Okay. So the coverage report will be getting here. Final, begin, real coverage, coverage report, and then how many passed and how many failed, and then module will be ended. Based on that, we are getting the coverage reports. Similarly, my scoreboard is comparing that actual values and expected values, right? So in that, my total packets, in that good packets, bad packets, I'm representing. So total packets are 1000, and then I'm writing, I'm getting past is 998, and then failed or bad packets, we are writing this one is 2 packets. Based on that, my scoreboard is displaying that some statistics. So this final block will gives you the reports. Okay. And also we are writing some opening a file and closing a file. Okay. So you opened a file, F open, dollar F open. Okay, in C language you have seen, right? Dollar F open, dollar F close, all these things. Okay, you open a file, simulation started, and then closing file will be occurred in your final block. Okay, you closed or not, and then this closing file will be taken care by this final block. Okay, so final block is gives you that closing time. Okay, some transaction statistics. How many are transmitted? How many are received? In that, how many are passing? How many are failing? All these things I want to write it in my statistics, module statistics, int transmission count, and repeating that transmission count and receiving count. Then final block I am writing the reports. Okay. So how many times you are repeating? 100 times. Then 100 tests are receiving here. You are repeating some 1000 times means this counts will be increasing for 1000 times. Okay. Same thing, object plus final blocks. That means you also are writing some handles like so class is the scoreboard handle. Based on that handle, you need to know how many pass and how many fails. And then we are writing the report here. Same thing report we are getting it the final block. Previously, I am writing that report in my final block. Now I have written that final report in my class only. Whatever the function I have written, that function I am calling in my final block. Okay. Through the handle, we are calling this report. So delays are not allowed in your final block because I told you after dollar finish there is no time delays allowed because it is executing zero simulation time only. Okay, that is illegal. So whatever the delays you are writing after the final block, okay, during the final block, these are all executed at t equal to 0. That means simulation ended some 1000 time you are mentioning. Then after that, it is not getting this 1010 data. Okay, not going for 1010 because you called already dollar finish. Then the simulation is ended there only. Here this final block is for just for reporting purpose only. Okay, and also some clock edges or waiting events you don't write it. Any wait conditions also not possible. Wait condition means some simulation consuming time, right? The time is consuming for the simulation. So then that is not allowed. Hmm. Why timing controls are illegal? Because where should 100 time units comes from, that is impossible. See, this is the final block, so therefore no delays are allowed. That means simulation already ended. Simulation is already ended. Then in your final block you are giving the delay means it's not possible to end that. Okay. See, initial begin block 0 time only it is executing. and then final block after dollar finish it is executing. So once the dollar finish is there means the simulation is ended. After that there is no further delays. Okay, so that's what. See here also we are getting some coverage reports, all these things. Okay, see just I am writing the initial begin block, dollar display started and ended, this dollar finish called, then go for the final block. There is no time delay. Okay, just see this one summary. Hmm. See, this is the final block execution. See, packet sent, packet received, and coverage report. I some FD final demo. Okay. So based on that initial begin block, simulation is started here. Okay, and then file will be opened for that, and then generated some activities here. Repeat of 5 times. How many packets will be there? So that will be sending here. If packet is not equal to 3, the packets received will be increased or error counts will be increased, and then dollar finish the packet send count, and then files open. FD means that is final block report. This final block report will be printing here, and then final block 1. So multiple final blocks also we will consider, right? In the final block 1, I am writing the simulation time, packet sent, packets received, errors, and coverage report also. In the block 2, error counts equal to 0, the result will be pass, otherwise the result will be fail. And then final block 3, so I am closing my file. Here I am opening the file, right? So opening the file, where is that opening the file? This is the FD opening the file. File data is open. In block 4, I am calling that block 3, I am calling that file is closed. And then in final block, I am receiving all the packets sent and received count will be there. That means memory cleaning is done. Okay, just run this code. See, the simulation reports will be getting clear like this. Packet sent 1, 2, 3, 5 times you are repeating, right? See, repeat of 5. 5 times you are repeating, then this packet count will be repeating for 5 times. Okay, so then simulation is started, then simulation is started, and then I'm getting that packets count is equals to 5, and then simulation will be ended at final block where we are calling this dollar finish. See, dollar finish I called here. Okay, each and every time some the time seconds I'm taking 1 nanosecond by 1 picosecond, right? That means 1000 delay is added for every time. Then it is reaching that 5 counts, then 10,000. Based on that the values will be, see, 1000, 10,000 here. So 10 will be there, right? So 10 is there means 10,000, 20,000, 30,000, 40,000, and 50,000. So 5 times I am repeating the same thing. And then delay is giving 20 here. That means another 20,000 is added. Then dollar finish will be called at 70,000. See the report, I got it. So what is the report? Simulation report. Simulation time 70,000. Packets sent 5, and then packets received 4, and then error count is 1. Then result will be failed. In this way the report will be coming. Okay. So the final block will be taking place here. This final block, whatever the reports you are writing, all the reports will be placed. Clear? Okay. The next class we will see that another topics.